In this lecture, I'm going to talk about pedestrian traffic flow characteristics. So the first thing to look into is how can we actually measure pedestrian traffic? Pedestrian traffic is very similar to vehicular traffic in the sense that we can measure it using flow, we can measure it using density and speed, very similar to what we've done and learned before in the previous lectures. But there are some interesting and fundamental differences as well. So there are many different ways of measuring pedestrian traffic, actually. Many different ways of measuring flow, density, and speed when it comes to pedestrian traffic. So the first one on top is a very classical way of measuring traffic, where we imagine we have a corridor where I have two directionals. It's a bidirectional stream. Some pedestrians are going this way, some pedestrians are going this way. You know, it's a mix of bidirectional stream. And if I want to calculate flow and speed, I can draw a line at any point in the section at location X, let's say, and just count how many pedestrians actually pass this line either way, either to the left or to the right. So that number n is representing the number of pedestrians that actually cross this line in any direction, divided by the time interval that I'm interested. So it will give me a measure of flow, which is pedestrian per unit of time, right? How can I calculate the speed here? I can look at instantaneous speeds and take a arithmetic average. So if for any pedestrian that crosses this line, if I measure the instantaneous speed of that pedestrian, VI, and if I just take the arithmetic mean of it, that would give me the average speed of the pedestrians. If we calculate flow and speed like this, interestingly, there is a drawback, and that is the traffic flow fundamental identity will not hold here. Q will not be equal to KV. I'm going to talk more about what is the better way of calculating and measuring these pedestrian traffic variables that will be consistent with the traffic flow fundamental identity in a minute. So the second way is actually, instead of drawing a line, how about we draw two lines and identify an area for the measurements with widths of B and depths of delta X, let's say. So here, I can actually calculate densities. It's an easy way of calculating densities, which is if we take the integral of the number of vehicles that actually pass through this area over time. So you see B multiplied delta X is actually the area. So this is delta X, this is B. So that gives me the area of this rectangle. So N over this B delta X, if I take the integral of that over time, depending on how my measurement time, and divided by that delta T, it will give me the density, which is basically the number of pedestrians over, instead of length, this time I have area. So in this case, it would be, for example, density would be, for example, X number of pedestrians divided by, for example, a square meter, right? It's no longer length. Remember, in car traffic, density was number of vehicles divided by kilometer or meter. It was only one length of a unit. But when it comes to pedestrians, because pedestrians can move multidirectional, there's no lane. It's not unlike car traffic. Pedestrians can move in any direction. The density can actually be calculated as pedestrian over the number of pedestrians over the area instead of one length. So it would be a square meter in this case. And then if I want to calculate the speed, what I can do is I can say every pedestrian actually crosses this delta X. So I just need to calculate how long it takes for every pedestrian to cross this delta X. So this delta X remains fixed for everybody, but delta TI changes pedestrian by pedestrian. So I would say each individual pedestrian will take the speed of each individual pedestrian would be delta x divided by how long it takes to cross this area. This is also not exactly correct because VI here in this way is underestimated, mainly because distance traveled by pedestrian is assumed fixed. So this delta x is assumed fixed. It is assumed that every pedestrian will exactly, the distance traveled by every pedestrian through this area is exactly delta x, which is not exactly correct because a pedestrian may actually go this way, for example, to cross this area. So then this distance traveled is longer than, if I call this L is larger than delta x, right? Because it has an angle. If L was totally horizontal, then L would be equal to delta x. But in this case, if pedestrians try to move a little bit to the left or to the right when it comes to crossing that bound area, L would be greater than delta x. So if we assume delta x is the same for every pedestrian, this way of calculating the speed of pedestrians is slightly incorrect, or has an error. Let's say it's underestimating the actual distance. So another way of calculating is the third way of calculating or measuring pedestrian traffic is we still use the same speed as we talked before. But when it comes to calculation of density, we don't take the integral over space, over time, sorry. We only actually count the number of pedestrians over the area. So in this case, if I want to calculate density at this specific snapshot of time, I would just count the number of people. So this is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, and maybe this guy 20. So K here would be 20 divided by delta x b. So density would be 20. So I'm not looking at, I'm not integrating density over time. I'm just assuming this number of pedestrians will remain the same for whatever delta t that I'm doing the measurement of density. So because of this, a specific way of calculating density, which doesn't necessarily take into account that n could change over time as well, even within that time period that I'm doing the measurement, again, the traffic flow fundamental identity will not hold here. There is a fourth method that is proposed by some of our colleagues in Germany, Stefan and Seyfried, that is published in 2010. And they say, how about we look at each individual pedestrian and try to calculate some local measurements around each pedestrian. So in this case, they use something called a Voronoi diagram, which basically says if I have an area and these are some points in it or pedestrians, I can specify a space around each pedestrian. And then I can measure the local density for each pedestrian separately, depending on how large or how much space this pedestrian has around it. So look at this diagram here, this green, red diagram here. All these polygons you see is the Voronoi diagram around each pedestrian. So in areas where there's a lot of pedestrians, the Voronoi diagrams around each pedestrian is a small, where, for example, here the density is a little bit smaller. You can see the polygons are larger as well. So the way the local density measurement is calculated here, so let's call this a local density, this PI. It is basically 1 over the area, 1 over the size of the area of this polygon for each individual pedestrian. So I have a local density measurement for every single pedestrian in this case, which is 1 over the area of the polygon around that pedestrian. And then if I want to calculate the total density for the whole corridor, let's say, or for any specific delta x in the corridor, I would just sum the p's, sum the local density measurements around each pedestrian, or take the integral over delta x. This is basically equal to summing all the px's, right? Divided by the total area of this area of the measurement. If I'm looking at the entire corridor, I can get this A in the denominator is the area of the corridor, or the area of any delta x multiplied by B. So this would be delta x multiplied by b here. So this is another way of doing the pedestrian traffic measurements. Again, this is very interesting. This is very innovative. It looks at the variations of the air space available around each individual pedestrian. But again, this is also not consistent with the traffic flow fundamental identity. So if you calculate QKV here with this method, still the traffic flow fundamental identity will not hold. That leads us to the next part, which talks about Edie's definition as the most and the only correct way of calculating traffic measurements, whether in pedestrian traffic or car traffic. So let's, again, what I'm going to talk about now is on measuring traffic, again, either pedestrian or car traffic, okay? Let's have a look at this time and space diagram where I have time on the x-axis and distance on the y-axis. And if I have some trajectories, I can specify any region or any area in this time and space diagram and calculate flow and density using these definitions that I have expressed here that are known as Edie's definitions because it was originally proposed by a guy called Edie's in 1965, which says if I want to calculate flow within this gray area in the time and space diagram, flow is simply the summation of the distance traveled by all the trajectories within that area divided by the area of that region. And density is actually equal to the summation of all the travel times of trajectories within this region divided by the area of the gray region here. So for example, in this case, let's have a closer look. Let me erase this circle that I drew around my time and space diagram, and also this lines here. So in this area, in this region, whatever that area is, let's say we can get it in the denominator, but I want to show you what is the summation of the distance traveled. So this trajectory, what is the distance traveled of this trajectory within this region? It's actually from here to here, right? Let's call it D1. So this is the distance traveled of this trajectory. The distance traveled by this trajectory within this region is also from here to here. So let's call this D2. And the other trajectory is from here to here. So we can call that D3. And the fourth trajectory is going from here to here. So it would be here to here. So that would be D4. So this summation of the distance traveled would simply be D1 plus D2 plus D3 plus D4 divided by the area of the gray region. So that gives me the flow. And what would be the unit here, by the way? Let's have a look. So the area, so the denominator on the top is basically what? The distance traveled, right? So distance traveled is a unit of distance, right? So let's say meter. And what about the area of the region? The area of the region is simply time multiplied by x, right? So time multiplied by x. So it would be time multiplied by unit of distance. So meter by meter will cross out. So then the unit would be 1 over time, which is correct, right? So because flow is vehicles per time. So the unit is flow, I mean, past vehicles or pedestrians, doesn't matter. It doesn't have the denominator, it could be pedestrians or vehicles, right? It's over 1 over a unit of time. So the unit is correct. So we can make sure this calculation is also correct. But let's have a look at density. Density would be the summation of the travel times within that region divided by the area. So how can I get the travel times? Very similar to what I get for the distances that I projected into the y-axis. This time I need to project into the x-axis. So this is trajectory 1, the projection onto the x-axis. Let me erase this. So this gives me T1 or tau1, let's call it, so it doesn't get mixed with time. So tau1. The second trajectory the travel time is from this one is tau 2, and I can do the same for the third trajectory and the fourth trajectory. So if I sum tau 1 plus tau 2 plus tau 3 plus tau 4 divided by the area, this gives me the density. Again, let's have a look at the units and let's make sure it's correct. So the sum of the travel times, the unit is time. And what about the area? The area is time multiplied by distance, meter. So time will cross out, and the unit is 1/meter, which is correct. That's density. Density was vehicle per meter or pedestrians per meter, right? Again, let's first talk about vehicles, and then we can extend this to pedestrians, because in pedestrians, density is actually better measured by 1/square meter. In this case, it's 1/meter because this is more of a unidirectional trajectories that we're looking at. So this is called ED's definitions. Very important, guys. This is the most correct and consistent way of calculating flows and densities using trajectories. But we can extend this concept to 3D time space diagrams where pedestrians move, because pedestrians can move in multi-direction, right? So I can have, so this is a 3D time space diagram where I have X, I have Y, and I have time on the Z axis. And we can see how trajectories of pedestrians, because they move in multi-direction, they actually maneuver through this 3D plane. And if you look at this is the top view, this is the side view, a very interesting way of looking at the trajectories of pedestrians. A very interesting example is I don't know how many of you are familiar with this, but every year actually Muslims do a ritual in Saudi Arabia where they move around this little house, which we called Kaaba in Mecca, and they do 7 circles around it, okay? And from some of our colleagues in Saudi Arabia, we were able to get some GPS data that some of these pilgrims they're carrying. And if we look at this GPS data and plot it in a 3D time space diagram, so this is a 3D time space diagram, we could see that these trajectories are actually doing a spiral movement, right? So if I look at it from the top view, so if this is the top view of looking at this situation, and this is the black house in the middle, so people are doing this 7 circles. So here I can't see time, right? Because it's only, I'm looking at XY plane. But if I now look at the 3D time space diagram, as I have here, these circles will become spirals, right? And each color here represents one person that is carrying the GPS device. So it was a very interesting way of looking at how people move, calculate the speed. Again, same trajectories, same concepts as before. The slope of the trajectory gives me speed. When it comes to 3D time space diagrams, I can actually calculate the speed across X, calculate speed across Y, and then if I want to calculate the whole speed, it would be Vx power 2 plus Vy power 2, and then the square root of it, right? Because it depends what slope am I calculating here. I can calculate the slope with respect to X, or I can calculate the slope with respect to Y, and then I can calculate the speed going in lateral movement, speed going in longitudinal movement, and then if I calculate this Vx and Vy, I can easily then get the square root of the summation of the squares, and then get the total speed of the pedestrian in both directions, in both X and Y direction. So another way of looking at the 3D time space diagram with pedestrians, I have X and Y, and then Z-axis is time. And these are all the trajectories of every individual pedestrians, right? So now, if I want to extend ED's definitions, remember the ED's definitions so far, we're looking at the 2D time space diagram, where I have time and X only. And we said if I have trajectories, if I draw an area, I can actually calculate Q and K within this area. Q would be the summation of the distance traveled over the area, and density would be the summation of the travel times divided by the area. But if I extend this ED's definitions from a 2D time space diagram to a 3D time space diagram, I can actually revise these equations of EDs and come up with some new derivations, because now instead of having a 2D area, I have a volume here, right? Instead of an area, I have a volume. So I skipped that part. So here is how extending ED's definitions look like. So in this volume that I'm looking at, what would be density? Density would simply be the summation of the travel times of all pedestrians within this volume rather than area. So for example, for this pedestrian, how long it took this pedestrian to enter this volume and exit this space. So it would be the time it takes from this start point and the end point. Same with the other ones, how long it took for this pedestrian to get it in and out. So it would be the summation of the travel times passing through this 3D shape over, instead of the area, now I have to put the volume, which is simply the volume of this measurement area, the gray area. For simplicity, we can go with cubes because then it's easy to calculate the volume. But theoretically, it can actually be any shape. If you take a complicated shape, then it's harder to calculate the volume of it, right? But cube is easy. So the volume of the cube would simply be x multiplied by y multiplied by t, right? So if this is x, this is y, and this is t, the volume of the cube is here, the summation of the travel times is there. And now let's see what is the unit of this density. This is for pedestrians only, right? So because it's in 3D time and space diagram, it's specifically designed for pedestrian traffic measurement. So density would be time divided by, what is the unit of the volume here that I calculated? So it would be distance multiplied by distance multiplied by time, right? Because it's x multiplied by y multiplied by time. So time will cross out, so it would be 1 over a square meter, right? So which is perfectly consistent with how we talked about density measurements in pedestrian traffic, because it's multidirectional. Pedestrians they don't have to move in lanes, one directional lanes. They can move in a space, they can move in a plane. So the density would actually be number of pedestrians divided by a square meter rather than pedestrians divided by meter or kilometer. Same thing can happen for flows. Flow now simply would be the summation of the distance traveled inside this cube divided by the volume of the cube, x, y, t. And then again, if you look at the measurement of the flow here, it's interesting. So it would be very different to the previous methods that I talked about. So here would be a d1 plus d2 plus d3. In this case, I have 3 trajectories. So what is the distance traveled within this cube divided by x, y, t? And the unit is, this one would be in meter, and the denominator would be meter multiplied by time. So meter and meter will cross out, and what is the unit? It would be 1 over meter time. Interesting. Previously, we talked about flow as being vehicles per hour or pedestrians per hour, right? But in this case, because we have multi-directional movements, the flow would be, for example, n pedestrians over time, let's say over pedestrians per hour per meter. This is basically the width of a corridor that we were talking about. So the wider the corridor that pedestrians are moving in, the larger the total flow would be, right? It's very similar to number of lanes. Remember, when it was in vehicular traffic measurement, we could say flow can be calculated as vehicle per hour per lane, right? Per lane, depending on how many lanes does it have. But because in pedestrian, we don't really have lanes, instead of number of lanes, we have this width of the corridor that pedestrians are moving in. So the flow can simply be representing this whole environment. So it would be pedestrian divided by time. Instead of per lane, it would be per meter of the widths. So that's the very interesting difference between pedestrian traffic and vehicular traffic, and how ED's definitions from vehicular traffic can be extended to AD's definitions from car traffic can be extended to pedestrian traffic. This is basically what I just talked about, and let's now try and have a look at the fundamental diagram of pedestrians. So again, imagine we have this corridor that people are going in two directions, and I want to calculate the measure. I want to calculate flow and density inside an area. Okay, if this area is small enough, that can represent the fundamental diagram of pedestrians. So in this case, if I measure imagine I draw this area for my measurement, so which would be delta x multiplied by b. So I want to do all the measurements within this area using AD's definition. So I calculate flow, I calculate density, and then if I want to calculate speed, I can easily use Q equal KV, the traffic flow fundamental identity, and then if I plot flow and density against each other for this specific area that I'm calculating the flow and density with AD's definitions, I get the fundamental diagram. If this area is large, if I make the measurement area large, I get something that is usually known as macroscopic fundamental diagram. While if I make this measurement area small, if this delta x is very tiny, then I'll get the fundamental diagram. So the difference between fundamental diagram and macroscopic fundamental diagram in this case is that the fundamental diagram is usually measured for a very tiny delta x area, while the MFD or macroscopic fundamental diagram is measured for a larger area. So in this case, let's say for the whole corridor, if I want to calculate it. So if you want to use the AD's definitions, for example, if you want to calculate flow, then flow would be the summation of the distance traveled by all trajectories. So this is for the FD, multiplied by the volume of the measurement. So in this case, it would be delta x bt. If I want to calculate MFD, if I want to calculate flows over the entire corridor, it would be the summation of the distance traveled for the entire corridor. Instead of delta x multiplied bt, I should put the length of the corridor. So it would be the length of the corridor multiplied by width of the corridor multiplied by the t. So this gives me the flow, the average flow for the whole, measured over the whole corridor, while this one is the average flow for this tiny little area that I'm doing the measurement. I talk more about macroscopic fundamental diagram for car traffic next week, but for now, keep this difference between fundamental diagram and macroscopic fundamental diagram in mind, and we'll talk more about it. There are interesting phenomena happens in pedestrian traffic, interestingly, that, for example, there is a phenomena called self-organization phenomena that although we don't really have lanes in pedestrian traffic, but lanes naturally forms. We call them self-organized lanes. Imagine it bidirectional movement. The red pedestrians are going this way, blue pedestrians are going this way. And if you look at it over time, so this is T1, this is T2, this is T3, snapshots from air, you can see that pedestrians actually naturally form some dynamic lanes. So these blue pedestrians are forming actually a lane that they're following each other. The other side also doing the same thing, and the green, sorry, and the red pedestrians are actually forming some dynamic lanes for themselves as well. So in this case, we see two lanes forming here. At some time later, a few seconds later, we can see this dynamic lane is actually grown. There is a big lane in the middle. There is another lane on the side. And then over time, this dynamic lane is actually dissipating and shrinking because the stream is crossing and is dominating this area. So we call them dynamic lanes because they come and go. They're not necessarily stable, and they don't last for a long time. And they may happen anywhere in a space. So that's the beauty of pedestrian traffic, that this self-organization phenomena is really interesting. I mean, it's amazing to look how pedestrians move in a bidirectional area and how these dynamic lanes form and dissipate over time.